Thank you so much for the lovely introduction, and thank you to the organizers for having me here and allowing me this opportunity to deliver a popular talk here. Yeah, so the title of my talk is "What is Combinatorial Thinking?" I've tried to keep it at a level where it should be accessible to all of you. So if you know how to count, you should be able to follow this talk. So what is combinatorial thinking? Well, before that, does it make sense to you if I say that there are perhaps algebraic ways of thinking or analytic ways of thinking or geometric ways of thinking? Perhaps you've experienced some of this over the course of this summer school as well. Sometimes they've asked you to draw pictures and decide, some facts based on what pictures you're drawing. We are asking you to develop some geometric intuition. Sometimes we're insisting that you write things out precisely and see what follows from the algebraic definitions we're giving you and so on and so forth, right? Yesterday's worksheet had a problem where you had to figure out the behavior of n to the 5 by 20 plus n to the 7 or something like that. And all of you managed to approximate it by saying, no, it's bounded above by 1 by n squared, and therefore something happens. So that's sort of making estimates and bounding things by simpler functions that might be called analytic ways of thinking, right? So suppose you take away all of that. Suppose I don't give you any algebraic structure. There is no addition, subtraction to do. There is no geometric structure. There is no continuity. There is no topology. Okay. Then what is left? So there's no linear transformation, nothing like that. So the bare bones of mathematics, let's say. Just you have some sets, okay, and you have some functions between them, let's say. With just this much, what can you say? Suppose I have a set. At least if there is no structure to it, then there's still something that you can say about a set. Like what might you be able to say about a set? Like it's bounded or not, okay, but boundedness is also sort of like a geometric property, right? If you have a space where you can talk about distance and so on, then you might, yeah. But sure, let's talk about finite sets. Let me give you that. Then what's one immediate thing that you might be able to talk about? Number of elements in it. So you can count. So this is something that is always there with us. You can always count things. And the fundamental notion of combinatorial thinking, I would say, it's a simplification, just like how I simplified what algebraic or geometric or analytic thinking is. This is also a simplification, but it's a good first order approximation, I would say. So combinatorial thinking is to see a number and ask, is it the count of something? Okay. So I have a bunch of problems here, which might motivate what I mean by this. So let me start with the first one. Is this board is visible to everyone at the back, right? Yeah. All right. Great. So let's ask for this. So here's problem one. How many subsets are there of a set of size n? Two to the power n. Okay, brilliant. So the answer is clear. How did you count this? Okay, very nice. So here's a simple way to count how many subsets are. Rather than saying, okay, let me enumerate all the subsets and then figure it out. You're giving me an algorithm which goes like this, right? So can you repeat that? Great. So the solution goes like each, let's say, of a set X, let's say, of size n. Each X and X is either chosen to be in the subset or not. Right? Each choice gives you a distinct subset. And we have 2 to the n choices in all. Right? So for each x, you make the choice. I either pick it or I don't pick it. The first one, I either pick or I don't pick. The second one, I pick or I don't pick. Each such combination of choices gives me one subset. Each distinct choice, each distinct combination of choices gives me a distinct subset. Okay, so that's one way. And given a subset, of course, it corresponds to some choice of picking and non-picking. All right, so that, excellent. So there is another set which is also counted in exactly the same way. So let me point out to you that the set of all sequences of, let's say, set of all 0, 1 sequences of length n also has size 2 to the power n. Is this correct? So when I say 0, 1 sequence, I mean, okay, sequence of length n, each entry is either a 0 or a 1. Do you agree that this is also 2 power n? Okay. So it's the same number. Does that mean that you can count subsets of size n using sequences, 0, 1 sequences? I mean, of course, individually you can count this, individually you can count that, but is there sort of combinatorial reason for why these two have the same size? Say I give you a sequence 0, 0, 1, 1, 0. So this is a sequence of length 5, 0, 1 sequence of length 5. Does it correspond to some subset of a set of size 5? Yeah, so how would you construct such a subset? Somebody said yes over here. Yeah. Perfect. So what we can do is the following. So if given this might correspond to, so let's fix a set X, right? So let's say X is the set 1, 2, 3, 4, 5. Right? We ordered it in this fashion. So if you pick the sequence, then this corresponds to the set, the subset, which I have not picked 1, I have not picked 2, I picked 3, I picked 4, I didn't pick 5. Right? This corresponds to the set, subset 3, 4. And vice versa. If I give you some subset, you can write down the sequence. Does that make sense? So without doing a separate count, without even knowing that the answer was 2 to the n, I could have given this bijection, you see? I needn't have counted that, oh, there are 2 power n many subsets of a set of size n, and there are also 2 power n sequences. That was not relevant for giving this bijection. So here are some more instances of the same thing. Let me see if they also tickle your fancy. Okay, so it's all right. Okay, so show that there are equally many even sized and odd sized subsets of a set of size n. You take the collection of all subsets of even size, take the collection of all subsets of odd size. These two collections have the same size. First of all, is this true? Some of you are sure of it, some of you may be still thinking about it. So empty set has size 0. 0 is even. Yes. No, I mean, well, what happens if n is 0? Well, this is of course the empty set. So how many subsets are there of the empty set? Empty set. Well, you have this, right? If X is empty, then the power set of X This of what do you say? Oh yeah, sure, that's right. Yeah. That's right. N is at least 1. Sure. Yeah. Good. Thanks. Any guesses? How many are there? Okay, let me not ask you to give a prediction immediately. How many are there? How many even size subsets are there of a set of sizing? Is that clear? No? Okay, so maybe we should start with that then. Not an issue. Can I use this? All right, so let's say E is the set of all subsets of X such that the size of E is 0 mod 2, right? So what is this? So, well, it has even size, so maybe it's of size 0. So there are n choose 0 many ways of picking such subsets, or maybe it's of size 2, so it's this, or it's of size 4, and so on. Correct? Okay. Similarly, if this is the set of all subsets of odd size, then this would be n choose 1 plus n choose 3, and so on. Maybe one more. Is that right? Okay. This is okay. 2 bar n minus 1. Somebody said, okay, thank you. How did you figure that out? Can you expand? That's an excellent answer. Yeah. Wonderful. Yeah. Tell me. Yeah. Yeah. So here's an answer, which is a purely algebraic answer, which is lovely. Okay. 1 plus x power n. Perfect. So that's n choose 0 plus n choose 1 times x plus n choose 2 times x squared, so on and so forth. N choose n times x to the n. Okay. Excellent. Very good. That's minus 1 to the n, n choose n. Okay. And subtract. Or just take all the negative terms to that side. Does that also make sense? Yeah. So what you gave is an exact answer for this by also setting x equal to 1 and adding. So two power n minus 1. Okay. But also, I mean, if you just take this to the other side, you see n choose all the negative terms to the other side. You get n choose 0 plus n choose 2 plus n choose 4 and so on is n choose 1 plus n choose 3 plus n choose 5 and so on. Now this is the size of set of all even size subsets. This is the set of size of the set of all odd size subsets. Very nice. But this is algebraic. I want a combinatorial proof. When I say combinatorial proof, I mean that when you see these numbers, when you see numbers like these, then they represent the counts of certain things, right? So without even knowing that n choose k counts the number of k size subsets of n, this proof works. Okay, but suppose we want to use that knowledge. Can you give me a map from E to O, which is a bijection? You know what a bijection is, right? Like 1 to 1 and on to. Should be injective and surjective. Now that you have proved that the sizes are the same, theoretically it's possible. Of course you can give it. Both of them have the same size, so there is a bijection. But is there a natural way to do it in some sense, some naturally combinatorially natural way? I think Aditya had some maybe partial answer to this. So if n is odd, here is one observation. So if n is odd, Aditya says, choose the map which sends any set A to its complement, A complement inside X, so X minus A. So if the total number of elements has odd size, then you can take an even set, its complement is an odd size set. So this gives you a map. For each even size subset, you get a corresponding odd size subset. And this is a pairing, correct? So this gives you the answer when n is odd. It doesn't work when n is even, because then if you take the complement, you got, for an even set, you'll get an even complement. So this is part way there. So let me give you one hint maybe, or okay. So what you can do is the following. You can flip one bit. Okay, you can fix an x in capital X. Okay, so in fact you can just take the first element if you wish. So what your map will do is the following. If X is in your set A, remove it. If X is not in your set A, you delete it. If X is not in your set A, you add it. Does that make sense? So the map F, it goes from E to O, does the following. It sends A to A minus X if X is in A, and it sends it to A union X if X is not in. I claim this works. First thing to check, suppose it is an even size set, right? Starting with an even size set, will this always give me an odd sized set? Right? Because you are either deleting one element or adding one element. So whatever it is, you're getting an odd size set. I'm saying that this is also a bijection. Means you can find an inverse for this. If I give you an odd size set, it can only come from a unique guy over here. Which one is that? Perfect. Exactly. So what's the inverse of this? So the inverse would be O to E, which sends, if you starting with an odd size set, it goes to correct if X is not in B, and B minus X if X is in B. Perfect. Same process in reverse. All right. Notice what is going on over here. So what you have done is you have not counted exactly what the sizes of either of these sets are. Without knowing how many there are of each, you have shown that they are equinumerous. Okay. So this is often a feature of combinatorial proofs, that rather than trying to work out exactly what an exact formula for a collection of objects that you're interested in counting, you show that whatever they are also counted by something else which you know how to count. Okay. You may not know, in fact, sometimes what the exact numbers are, but you know that both of them have the same size. Okay. All right. So this was. Let me give you maybe a smaller sort of example of the same of a similar fashion, and then I'll move to a very cute example from graph theory. Okay. So yes. Yeah. Yes. Yeah.
If we take 0 to n being
No, maybe I didn't follow the last part of what you said.
like if you have one,
Yeah.
that means that there'll be 2 odd.
That's right.
So you get a half of.
Oh, that's a very interesting way of putting it. You're saying to pick a subset uniformly at random, and because there are equally number of even and odd size elements. Yeah, maybe you'll have to do a quick check that it works out, but yeah, that's a very interesting way of arguing. Yeah, very nice. Yeah. Okay, so here's one last, maybe a teaser of the similar kind. Before I show you a very interesting such bijection which comes in graph theory. Okay, so what's this? You know what n choose 2 is, right? Now you've seen all the other binomial questions. What is n choose 2? What does it count? I mean, when I ask what is n choose 2, I don't want the formula. I mean, what does it count? Number of ways of picking a set of 2 elements out of a collection of n elements. All right, so that's n choose 2. But curiously, this is also this, right? 1 plus 2 plus 3 plus n minus 1, you know, formula for an AP. Yeah. This is n minus 1 into n by 2, right? That also turns out to be n choose 2. Can you give me a combinatorial proof of this? So what I've written is n choose 2 is 1 plus 2 plus 3 plus da 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 n minus 1. You agree? So sum of the first n minus 1 integers is n minus 1 into n by 2. That also turns out to be n choose 2. Can you give a combinatorial proof of this? You have said that the left hand side counts the number of 2 element subsets of a set of size n. What does the right hand side count? Very good. So you have to pick it in a certain order in order to justify this. Yeah, so it's more or less what you're saying. So what she's saying is maybe what this is doing is you're trying to figure out how many times a certain element has to be repeatedly picked while you're picking 2 elements. Is that fair rephrasing of what you said? Perhaps not. Okay. I'm sorry about that. Okay. No matter. So what I would like you to do here is not find something else to count. Okay. Take the same collection, count it a different way. This is what is typically called a double counting argument. Okay. So the same set, you know what this is, right? So n choose 2 counts. N choose 2 is the size of set of all AB. Yeah. Let me just finish writing this. Yeah, fine. Yeah. Subsets of set A is not equal to B. Is that right? Yeah. Please tell me. Very nice, very nice, beautiful. So here is her double counting argument. So this set of all 2 element subsets is counted by n choose 2, sure. But how can you pick these guys? She's giving a algorithm to pick them. So she says first pick A to be 1. Okay. When A is 1, how many choices do you have for B? N minus 1 choices. Okay. So she's ordering them in the following way. So you pick 1, 2, 1, 3, and so on, all the way up to 1 n minus 1. So this is n minus 1 ways to do it. Then she says start by picking 2, then deciding what to pick next. Now you can't pick 1 because you already picked that over here. So you only start picking guys which are bigger than 2. So you 2, 3, all the way up to 2n minus 1. How many are there? Did I say something? Oh, 2n. Correct. Did I say 1n? 2n. Thank you. Yeah. Great. So these are n minus 1. These are n minus 2. All the way up to when the first element that you picked is n minus 1. You have only one choice for the last one. You have this. So this set, you counted it in a different way. This is a double counting argument. Very nice. Yeah. So this is n minus 1 plus n minus 2 plus 1 and so forth, which is equal to this. Good. So this is some flavor of what people do when they think combinatorially. You see some numbers and you ask, first of all, is it the count of something? And you see an equality and ask, is the same underlying set being counted in two different ways? These are sort of two very common questions that immediately pop into a combinatorialist's head, I suppose. So now for the promised graph theory double count. So time do I have? 24 minutes. I think that's plenty. Okay. So this sort of double counting, there is maybe one more very popular instance which I can probably show. I think I don't need this as well. Yeah. So I think you guys saw the Erdős-Srény graph at some point of time in the previous, maybe not case study, but maybe a couple of days ago. So you know what a graph is, right? I'm not going to be talking about random graphs, mostly trees, but you know what a graph is? Everybody knows what a graph is. Okay, so given a graph, so here's the next problem. Let's just do a quick warm up before I step into what I wanted to tell you. So let G be a graph with some vertex set and edge set. So when I say graph, I always mean finite, simple, undirected. Yeah. So all these nice properties. Okay. I beg your pardon? No loops, no multi-edges, that sort of stuff. Yeah. So exactly. So the edge set, is just a collection of two element subsets, not a multi-set. Yeah. Exactly. So take a finite, simple, undirected graph. Then if you sum all the degrees of the vertices, then this is 2 times the number of edges. Have you guys seen this before? Lots of people nodding their heads. All right. So how many of you have not seen this before? Okay, so that's still a substantial number. Great. So here is, you know what the degree of a vertex is? So the degree of a vertex is the number of edges which are incident at that vertex. So you sum that all up, it is 2 times the number of edges. Once again, this should be given some combinatorial proof. Exactly. So the right hand side certainly seems to be of that flavor. It's 2 times the number of edges. So maybe I'm counting the edge set twice in some way. And the left hand side is again some count of the edge set in a different way. Do you have some idea of how to do that? The left hand side as well? Yes. Is yours also correct? But what exactly are you counting? Yes. 2 as well, the same edge gets counted. Excellent. So here what you have done, both of you, great job, is that degree of V is what you have given the combinatorial interpretation, where earlier we were giving a combinatorial interpretation to these binomial coefficients. Now you have said that this degree of V, whatever this number is, actually it's the count of something. It's the count of the number of edges incident at V. So when I'm summing all the degrees, I'm counting how many edges are there at each V, at each vertex, and I'm doing it over every vertex. Okay, so that's the left-hand side count. Now there's another way to do it is to look at each edge and ask, in this process, how many times is it getting counted? Well, every edge is incident only to 2 vertices, right? So in this whole process, it gets counted once at this end and once at that end. When you're counting, if the edge is UV, it gets counted once when you're counting the edges incident at U. It gets counted once when you're, it gets counted again when you count the edges incident at V. Does that make sense? Is it clear to everyone? Yeah, so that's a double counting argument, and it's a very neat argument. So let me just maybe write it in short over here. So how do I want to say this? So V counts the number of edges incident at V, and each edge, let's say AB, is counted twice in this process. Exactly twice. The same collection, you counted it two different ways. Therefore, you have this equality. Very nice. All right. So that's enough time to step into this, I guess. Okay. So there's another very famous, this is also popularly called, I think, the handshaking lemma, because in some sense, each time you have a bunch of people who are shaking hands, if they're shook in a hand, you drop an edge into the corresponding graph. And you ask how many handshakes happened. It's a number of edges, right? So after you ask each person, how many people did you shake hands with? That's the sum of the degrees. And then whatever that answer is, you divide by 2, because if I've shaken hands with you, you've also shaken hands with me. So you counted the number of handshakes 2 times. Yeah. So that's why it's also called the handshaking lemma. Okay. So all right. Next, do you know what a tree is in graph? I mean, of course, you know what a tree is, but do you know what a tree in graph theory is? So if you draw a graph in which there are no cycles, then it's called a tree. Okay, a connected graph. Draw a connected graph in which there are no cycles, then you call it a tree. So for example, this is a tree. Let me draw it. This is a tree. Okay, so there are no cycles here, right? So this is a tree, and it's a connected graph. Okay, so what you can do is, okay, there are how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 vertices here. So you can label these vertices any way you like. Okay, and that will give you a labeled tree. So let me just do some random labeling. Okay, this is a label tree. You could change it up any way you like. That will give you some other label tree maybe. Okay, so the question is, how many label trees are there on n vertices? Okay, so how many label trees are there on n vertices? Maybe you should just do a few examples. So how many label trees are there on one vertex? Can you guys still see if I write here? No? They come here? So let's say n is the number of vertices. Tn is the number of label trees on n vertices. Okay. So if n is 1, how many label trees are there on exactly one vertex? Only one way. I mean, you have to give it the label 1. I mean, if there are n vertices, you label it using 1 to n, not arbitrary labels. Okay. So there is only one way to do this. Okay. Suppose there are two vertices. There's only one possible tree, first of all, on 2 vertices. You have to draw an edge. No, that's a tree must be connected. Yeah. So yeah. So if you have what you say disjoint chunks, right, like that, where this is also a tree, that is also a tree, then it's what is called a forest. It's a more general sort of a tree. So a tree is, for me, a tree is a connected graph. Connected means if you take any 2 vertices, I can go from one place to other place via a sequence of connected edges. Okay, so I can walk from here to here via edges. But if this was the whole thing, then I can never go from here to anything over there. So this is not a tree. Okay, so it's a connected graph without cycles. This is my definition of a tree. Okay, does that clarify the definition? Yeah, so you're thinking of objects that look like this, and you want to put labels on them. Okay, so there's only one possible tree, labeled tree on two vertices. Okay, so you get one over here. What about three? You have three vertices. How many trees can you make like this? There's only one way really. This is the only way, right? I mean, if you want me to do this also, is the same thing really. Correct? Correct? Okay, so how many ways are there to label this? Distinct ways to label this? Three ways. Because this vertex, depending on what label you put here, you'll get a different tree. So 1, 2, 3 is one possible way to do it. You could also do 2, 1, 3. You could also do, what did I do? 3 here, correct? 3, 1, 2. Because if I swap 1 and 3, it's the same tree in some sense. You're seeing that, right? I mean, it just depends on whether I do it like this or I do it like that. So up to these kinds of redrawings, which don't really fundamentally change it, how many label trees are there? That is the question. Okay, so for here you are getting 3. For 4, so there is, suppose you chose this as your labeling, right? 3, 2, 1. In this example itself, right? Or no, you want me to give a more general one? I'm saying there should not be an isomorphism between the two trees. So a bijection between the vertex sets also preserves incidences, such that labels are also preserved. Yeah. So label preserving vertex bijection, which preserves incidences. Yeah. So in this case, so it's not drawing dependent in some sense. That's what I'm trying to say. So I could have drawn the same label tree in this way or that way, depending on where I put the 3, but that doesn't really matter because I could have mapped this vertex here, and this one upstairs, and then I would essentially get a bijection. So that's what I mean. So this doesn't really count. Does that help? Thanks. Okay, so we could do this process. I don't think I have enough space for 4 and 5 on the board here because they blow up quite soon. So I believe this is 16, if I'm not wrong. And this is 125. And fairly soon it starts becoming pretty big. So what happened is, there is a very neat result due to Kelly, which gives an exact formula for how many such label trees are there. So Kelly's formula, very celebrated one, is the number of label trees on n vertices is n to the power n minus 2, exactly. Okay, n to the power n minus 2. Now already your combinatorial sixth sense should start tingling. What does n to the power n minus 2 count? Do you know some natural set that is counted by n to the power n minus 2? We did this like 2 power n. What does 2 power n counted by? I mean, you said all sequences, 0, 1 sequences of length n, right? So 3 power n is all length n sequences in which each entry can take the values 1, 2 or 3. N power n minus 2 would be therefore n minus 2 length sequences, which each entry could be anything from 1 to n. Agreed? Okay. So now you have a bunch of very nicely labeled combinatorial objects, all these labeled trees, and you have this collection of n minus 2 length sequences. Is there a natural combinatorial bijection between them? Okay, that's the question. So I will give you the bijection by example, and you guys can think about whether you're convinced or not, and whether you can develop it into a proof. All right, so does that make sense? What I'm saying is, n to the power n minus 2 is also the number of n minus 2 length sequences over 1 to n. And now the question is there a correspondence between this set of sequences and the set of all label trees? So let's try and develop such a correspondence. Oh, damn it, I erased this. It's going to be my example. Okay, no matter, we'll build another one. Right, let me pick the example I picked over here. What do I have here? Does that make sense? I guess I missed a 9. Yeah, sure. I mean, let's just put this to make it the same. Three, 4, 5, 6, 7, 8. Okay, so this is a tree on 8 vertices. Rather, this is a tree on 8 vertices. What I'm going to do now is, given this tree on 8 vertices, I'm going to give you a sequence of length 6, right? Because it's n minus 2 length sequences. So I'm going to give you a sequence of length 6 whose entries lie between, whose each entry is one among 1 to 8. Okay. So here's how I'm going to build it. What I'm going to do is I'm going to look at the leaves. Okay. So pick the leaf with the smallest label and record its neighbor, because it has a unique neighbor. When I say a leaf, I mean a degree 1 vertex, things like this, 1, 2, 8, these are leaves, okay? So it has degree 1, so it has a unique neighbor. So first pick that leaf which has the smallest label, record its neighbor. So what is its neighbor? What is the, with the smallest label? It's this guy. Its neighbor is 4. So first thing I'm going to do is record 4 and delete this. Repeat the process. What is the leaf with the smallest label? 2. What is its neighbor? 4. So let's record 4 and delete this. Okay, next. Correct. 4 is a leaf and it is the guy with the least label. So its neighbor is it clear? So now 4 is a leaf with the least label among all the leaves. I will record the label of its neighbor. So 7. Then I delete this. Okay, next. 6. I'm not going to record 6. I'm going to record the neighbor of it. Then 5 is the one, so 3. Okay. Then correct. Among these two, this guy, so 7. Yeah. At this point, I stop. It's just an edge, right? Let it be. I have already got a sequence of length 6. This is what is called the proof or code for this tree. Okay. Now let's see how to go back. I mean, might as well get rid of this. Okay. So now we have forgotten what our original tree was. All you have is the code. And I hope some of you have noted down what the original graph was. Otherwise, you just have to believe me. So given this code, how are we going to get back to this? So we have our vertices, right? So let's just put them somewhere. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now from the code, I'll have to figure out what edges I'm supposed to have added back, right? Okay, so I have the vertices 1, 2, 3, 4, 5, 6, 7, 8, and this is my proof of code. So the first thing I'm going to do is look at the smallest vertex here, which does not appear here. 1, so join 1 to 4. In fact, maybe this diagram is probably a bad idea. Let me just build it step by step over here. So I'm sorry about that. Yeah. So I have 1 to 8, right? So far I've decided 1 to 4 is going to be an edge. Okay. So I picked the smallest label here, pick the smallest unused label, join it to the first element in my sequence. All right. Okay. So now let's get rid of this and let's get rid of this. Okay. So now this is now the first element of my code. What is the smallest unused element which does not appear in this sequence? 2. So join 2 to 4. Get rid of this, get rid of this. Okay. Does that make sense? Yeah, okay. So now this is reduced. What is the smallest element here which does not appear here? 3 appears, right? So somebody said 3, so that's not right. So 4 is there. So join 4 to 7. Then get rid of this, get rid of 4. Now you have 5, 3, and 7. What is the smallest element here which doesn't appear over here? 6. So join 6 to 5. So they are not yet here. So let's just join 6 to 5. Okay. So let's get rid of 6. What's the smallest element here which doesn't appear here? 5, right? Okay. So join 5 to 3. What's the smallest element here which doesn't appear here? 3. Join 3 to 7. Get rid of this. The only 2 elements left are 7 and 8. Join 7 and 8. Is this the tree that we started out with? Just check. Maybe it looks slightly different in the drawing, but it should be the right answer. And there you go. So this is a rather mind-blowing correspondence if you think about it. So say that again, yeah. When I'm obtaining the proof for code, right? Yeah. So I will look at the smallest label among the leaves, okay, and I will record its neighbor. Then I'll delete the leaf. So I recorded 4, I deleted this. Then I recorded 4, I deleted this. Then I recorded 7 and deleted this. Now among 8 and 6, the smallest label is 6, right? So then I recorded 5. So 8 and 6 are the leaves of the smaller tree after 1, 2, and 4 were deleted, correct? So they are not leaves. So leaves are the degree 1 vertices in the graph. So each time I'm going to pick a leaf to delete. Okay, so not 7, 3, and 5. I'm going to pick a leaf to delete. Okay, so after 1, 2, 3 rounds, I have this graph, right? 8, 7, 3, 5, 6 as a path. So only these 2 are the leaves. So among them, the one with the least label is 6. So I record 5, delete 6. Then 5 becomes a leaf. Then again it's a leaf, so I record 3, delete 5, and then so on and so forth. Does that make sense? Yeah, thank you. Good question. Any other questions? Because one question is, why does this work? But that's a do-it-yourself. So go back and think about it. Yeah, I guess that's all I have to say. Thank you so much. You've been a wonderful audience.
Any questions? Okay, so if there's no questions, let's thank the speaker again.